In this video, we discuss how to calculate the change in entropy in a chemical reaction in the context of the third law of thermodynamics. Alright, so far we have learned how to calculate changes in entropies for gas expansions, heating and cooling processes, and phase transitions. But of course, in chemistry and in the molecular sciences, we're interested in chemical reactions. We would like to predict whether a given chemical reaction is spontaneous or not, and that necessitates the calculation of the reaction entropies. Alright, so our reaction is going to be the combustion of methane at ambient conditions. Right, so at ambient conditions, methane is a gas, and we can burn it with oxygen, which is also a gas, to generate CO2, and then water, which under ambient conditions would be a liquid. Now, something that is very easy about the calculation of the reaction entropies is that predicting the sign of delta S is generally doable just by looking at the reaction. What we know is that according to positional entropy, gases are far more entropic than liquids and solids. Right? So you simply have to look at the gases and see whether you have more moles of gas in products or reagents. That alone is generally a great predictor for the sign of the change in entropy. In this reaction, we have 3 moles of gas in reagents and only 1 mole of gas in products. That means that you will be losing entropy, and delta S should be negative for this reaction. Alright, so again, the prediction is something that can be done without actually typing any numbers. Now the question is, how do we calculate that reaction entropy quantitatively? Well, notice that entropy is a state function. Therefore, for a chemical reaction, we simply need to figure out what the final point is and the initial point is, take the difference between those entropies, and that would be the change in entropy in the reaction. All right, so the final point in a reaction is products, the initial point is reagents, so the difference in entropy between products and reagents is directly what the change in entropy in the reaction is. Right, so the way to do this would be, well, the change in entropy in the chemical reaction, and this is generally going to be a molar entropy, and then at standard conditions generally, is simply going to be the sum of the entropies of products minus the entropies of reagents. And again, this stems from the fact that entropy is a state function, so the only thing that matters to calculate changes is the final state and the initial state. Our question then is, well, how do we come up with the entropies of products and reagents? Well, when we were doing the same thing but for enthalpies, we had to define an arbitrary zero for the enthalpies of formation that was called the formation enthalpies, right? So we said that the most stable allotropes of constituent elements had 0 enthalpy of formation, and then we defined the enthalpies of every single molecule with respect to that sea level. What happens with entropies? Well, with entropies we do something different, which is to recognize the third law. Okay, so here's what the third law says. When you have a pure and perfectly crystalline substance at 0 Kelvin, there's actually no dispersal of matter or dispersal of energies. Essentially, the number of microstates of a perfect crystal that is pure at 0 Kelvin is just 1. There's simply one energy state available to that system, and there's only one position available to the particles of that system. So under that set of conditions, again, a pure substance in a perfect crystal at 0 Kelvin, then if there's only one microstate, what that means is that the entropy is 0. Okay, because the microstates and the entropy are related by Boltzmann law, right? If you only have one microstate, one only possibility, right, then the entropy is 0. So that is the third law of thermodynamics, right? The question is, well, how is that useful? Well, the third law essentially tells you where the 0 is, and then what you can do is utilize that 0 to calculate what the absolute entropy of a substance is at conditions that you're interested in, right? So the idea here is that we're going to be running this reaction under ambient conditions. And what that means is that the temperature is 298 Kelvin, and then the pressure will be 1 atm. Okay? Now, the third law of thermodynamics refers to 0 Kelvin, right? So the idea is that, well, if we find a way to go from the 0 Kelvin to 298 Kelvin and calculate the change in entropy of that substance in that temperature, then we will be able to figure out what the entropies are at 298 Kelvin, and then use them for this particular reaction. Okay, so let me show you how that is done for one of the reagents or products in this reaction. In this case, we're going to be choosing molecular oxygen. All right, so here's the idea. This is a temperature, and this is how the entropy of O2 changes when we go through when we go from 0 Kelvin, which will be right here, to room temperature, which will be out here. Okay, so here's the idea. We know that if we have pure oxygen, and it's a crystalline substance, which it is, and we're at 0 Kelvin, the zero law of thermodynamics tells us that this entropy should be 0. It's going to be a molar entropy, so we're going to do joules per mole Kelvin. That is the third law. And then what we actually have to do then is see how the entropy changes when we get to 298 Kelvin. Obviously, the entropy is going to increase because we know that when you heat a substance, then the entropy increases. And obviously, we also know that oxygen at 288 Kelvin is a gas, and here at 0 Kelvin is going to be a solid. Right? So when you go from a solid to a gas, then the entropy also increases. Right? So what has to happen is that the entropy is going to increase. The question is, do we know exactly what that point is? Well, so this can be done, right? The first thing that is going to happen is that you're going to be heating the solid from 0 Celsius until it melts to liquid oxygen. And that happens to happen at about 54 Kelvin for oxygen at ambient pressure. Right? So this change in entropy is simply the gain in entropy when heating the solid from 0 Kelvin until the melting point, 54 Kelvin. At this point, what happens is that the solid oxygen turns into the liquid. That is an isothermal process, so the temperature doesn't change, but the entropy increases because you're going from the solid to the liquid, right? And at this point, now you have O2 as a liquid, right? So that is what we call the phase transition, which is fusion. And the entropy of fusion is positive. You're going from a solid to a liquid, which is intrinsically more disordered. Okay, so we have here so far two entropies. First, heating the solid from 0 to 54, and now melting the solid, or undergoing fusion of the solid to generate oxygen liquid. Then what we have to do is continue to heat that liquid until it gets to the boiling point, which for oxygen at ambient pressure happens to be at about 90 Kelvin or so. At this point, if you continue to increase the temperature, what will happen is that you will turn the liquid into a gas, and this actually will distort much more. The gain in entropy of this vaporization, right, turning the liquid into the gas, is actually much greater than turning the solid into the liquid. The gain in entropy is much greater. Okay, and then what happens is that after this, you will have your oxygen now as a gas, and then you have to bring it to 298 Kelvin, which is going to be right here. So let me trace that. And then that will just be heating the gas. Okay, so these are our steps. First, heat the solid from 0 Kelvin to the melting point. Then melt the solid into the liquid, heat the liquid from the melting point to the boiling point, vaporize that liquid, and then heat the resulting gas until you get to the temperature that you want. Okay, so because we know how to calculate this for any substance, notice that when heating and cooling, the change in entropy is simply equal to n times CPM natural log of T2 over T1 if the heat capacity is constant with temperature, and then the change in entropy in a phase transition is simply the change in enthalpy in the phase transition over the temperature at which that takes place. Right? We know how to calculate the change in entropy here, 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 and what that means is that if we know what the start is, 0 entropy according to the third law, then we can know for sure how much entropy is that for our substances. Okay, and it turns out that for oxygen, that happens to be 205 joules per mole Kelvin, right? And then we can write all of the entropies for the rest of the substances. Okay, so for methane gas will be 186 joules per mole Kelvin. That is the absolute molar entropy, the standard one at 298 Kelvin. For oxygen is 205 joules per mole Kelvin. For CO2, which is a gas, will be 214 joules per mole Kelvin, and then for water, which happens to be a liquid, at room temperature is about 70 joules per mole Kelvin. You can clearly see how the entropy of water, which is a liquid, is much, much lower than the entropy of any of the gases. Okay, and that's because intrinsically liquids are more ordered, they're less entropic than gases are. Okay, so with those numbers, we're now actually ready to calculate what the change in reaction entropy is for this combustion of methane at ambient conditions. Like we would say that the change in entropy in the reaction under standard conditions is just going to be the sum of the entropies of products minus reagents multiplied by the stoichiometric coefficients, right? So that will be the entropy of CO2 minus or plus 2 times the entropy of liquid water, 70 joules per mole Kelvin, and then minus the entropy of reagents, which is going to be the entropy of methane, 186 joules per mole Kelvin, plus 2 times the entropy of oxygen gas, 205 joules per mole Kelvin. Okay, you type that up in your calculator and you should find a change in entropy for this reaction of minus 242 joules per mole Kelvin. Important thing here is that that sign is negative, and that is exactly what we predicted simply based on the balance of moles of gas between reagents and products. Right, you go from 3 moles of gas in reagents to just 1 mole of gas in products, and that intrinsically means that you're ordering that system. There should be a decrease in the entropy, and that is beautifully borne out by our calculations. Right, so let's wrap up this video. In this video we have learned how to calculate the change in entropy in a chemical reaction. That is done simply by taking the entropies of products and reagents and taking the difference between them. Our question has been, well, how do we obtain those entropies of molecules, right, products and reagents? For that we have used the third law of thermodynamics, which tells us that if you have pure substances, they're perfectly crystalline and you're at 0 Kelvin, then the entropy should be 0. Okay? And then we simply take that 0 and then see how the entropy increases until you get to room temperature, which is where you want to work, and then find out what the entropy of that substance should be at room temperature, put that in tables, do it for every single substance that you're interested in, and then you're going to have tables for molar entropies of every molecule under ambient conditions. With those, you simply take the entropies of products minus reagents, and that should be the change in entropy in a chemical reaction.